Okay, so let's have a class, and we start to talk about the bacterial growth, and just remind you it's very important we talk about the bacterial growth curve, and the growth curve looks like this is a x-axis is time, y-axis is cell population, and first of all, it's not linear, it is a curved. So we have four curves like here. So preparation, lag phase, log phase, they start to grow dramatically. And the stationary phase, because in the environment, their toxication material and their nutrients are balanced by the time. And at the end, they start to die. So death phase, because the toxication material is dominant. So that is a very important growth curve. We have to know about this. Okay, so I'll just move this off. Okay. Next, we talk about impacts from the, we can say it's an external impacts for the microorganism growth. This is including the pH. pH can classify the acidophiles, neutrophils, alkalophile. Then we talk about acid-resistant bacteria, because acid-resistant bacteria could cause cross-protection. So it's generally the problem for the food industry. Then we talk about the temperature. Bacteria, they always have a maximal and minimal temperature, but there's the optimal temperature they can grow. Most of the bacteria in the lab is 35 degrees Celsius and grow 24 hours. Based on the temperature, we could categorize them into the psychrophiles, psychotrophs, mesophiles, thermophiles, and hyperthermophiles. And we talk about most of the bacteria is mesophiles, Bacillus is thermophiles, and hyperthermophiles is environmental bacteria, and we can see that in hot springs at Yellowstone National Park. And the psychotrophs, this guy gives us a lot of trouble for the food and microbial safety, because they can grow in the refrigerator temperature. So let's say Listeria monocytogenes, and we will mention detail later on. Psychrophiles basically is in the deep marine ocean area. That is also environmental bacteria. So we have a different range of the temperature, and you guys don't have to remember it. If there is, you just find it in the slides. The major students, they usually have required to remember that. Okay, water activity. This guy, we could talk about 15 minutes. This one is a little bit tricky concept. There are some physics behind it, so we want to talk about it. This comes out with a very simple question. I ask my graduate students, because they are doing the research. They already finished a bachelor degree. They should know. What is water activity? Then one of my students just come out saying the amount of the water is water activity in a food product. But that is wrong. So I want to let you know is that the amount of water, let's say in foods, what is this one? This is a moisture content. This is not water activity. Water activity is what? This is a little bit of physics behind it. This equals, I'll just move down because I need to explain to you. Okay, water activity using AW. Z equals partial vapor pressure above a food product and partial vapor pressure above a pure water. This sounds not very easy to understand. So what it is, we're gonna talk to you and explain to you. Okay, let's talk about the bottom first. I have a closed vessel, or a closed bottle, let's just say like that. Okay. The closed vessel like this. And I put water there. Okay, this is the water. H2O, water. Okay, by the way, water molecule looks like this. So this is, you learned in chemistry. This is a so-called covalent bond. This angle is 104.5. This distance 0.1 nanometer. Is that right? That's the structure. Okay. Once you have water there, the water will be jumping out of the interspace between the air and the water. That is called evaporate. So the water molecule goes out. Let's say water molecule goes out. The water molecule also going to go back. So what we say, condensation. When the time goes on, they will reach an equilibrium status, which means evaporation and condensation will be equal. Therefore, they generate a pressure. This is called vapor pressure. And the vapor pressure is affected by temperature. This is, everybody knows. So what happened? If I have a heater here, okay, I have a fire here, let's say. I heated this closed vessel. The water starts bubbling, is that right? Once the vapor pressure equals atmosphere pressure, if this equals, what will happen? The boiling will happen. Is that right? The water starts boiling. And we also learned that the boiling depended on what? The elevation. So this is degrees Celsius. At sea level, what's the boiling temperature? 100 degrees Celsius. It's like this. What's the boiling temperature at West Virginia? We are at Appalachian mountain area. Our boiling temperature around 94 degrees Celsius. At Colorado, let's say Rocky Mountain National Park, right here, around 80 to 85 degrees Celsius. How about Everest, the highest mountain in Nepal and China, 70 degrees Celsius. So this gives you a food safety problem. If you put an egg in the higher mountain area, maybe 85 degrees Celsius or 70 degrees Celsius, they start to boiling. Does that mean it's going to kill bacteria? Maybe not. Okay, so that's just one little let you know. So atmosphere pressure. So one standard atmosphere pressure equals 1.05 multiplied by 10 to the 5 Pascal. Is that right? That's in your physics class. You may talk about that. Okay, so that's pure water. Let's say I have another closed vessel right here. And this is the food products. In the food products, what we have? we have salt. We have sugar, carbohydrates. We have like protein. These are macromolecules. So once there, we also have a water. They're gonna impact it. I mean, the water gonna go out. The water gonna go out. But they are not gonna be that much because sodium chloride, the sugar and the protein, they are dragging them down. So therefore, the vapor pressure in a food products is always less than a pure water. So that's a vapor pressure. So what are the examples of the water activity? If you have a hot dog, 0.995. That's why hot dog is easily to be contaminated with pathogen, because water activity is higher. In other words, this means available water to be used by bacteria. How about beef jerky? Little bit dry, 0.900. How about, let's say, chewy chocolate ball? You like that, chewy chocolate ball? 0.50. How about chips? Dry food products, very low water activity, 0.25. Okay, now we go back to the question. You said amount of the water in a food is moisture content, then you have a water activity. So what's the relationship between that? Yeah, that's a very simple question, but it's difficult to understand. We have a curve for that. What's a curve looks like? This is called a absorption curve. X-axis is water activity. If water activity multiplied by 100, that equals relatively humidity. And we also call it equilibrium relatively humidity because a food products, you're going to absorb the water, desorption water, at the end of the day we'll reach a balance. And the y-axis is equilibrium moisture content. So you get a curve. What's the absorption curve looks like? It looks like this. Yeah. What's the desorption curve looks like? It looks like that. So always remember, food products, when they absorb and desorption water, is not going to be reversible. And we hope it's reversible. Why? Because food safety is never a problem. When you like to, let's say this is beef. I want to eat it, I eat it. I don't want to eat it, I'm dragging all of the water out. Then whenever I used, I put all the water back, but it's not going to happen because it's not reversible. So based on this, we could be categorizing them into a different layer. This is, we call it a monolayer. In your chemistry class, this is called a bound water. And this is called additional layer. And the last one we call it a capillary water. So what are the food products fit this category? Monolayer chips. Additional layer fruit roll up. How about the capillary water? Meat and produce. So why the student have the impression the water activity and the moisture content are the same thing? Because when we talk about the meat, we talk about the produce, it's in the last category. In the capillary water is a major component. That highly correlated with water activity and moisture content, but they're not the same. So, give you some of the other things we want to mention. Did you ever heard about there's an outbreak of chips? No. You never heard about there's a breaking news today, 500,000 pounds of chips is recorded because of listeria outbreaks. No. Because if the food products like that, we care about is lipids of oxidation. So what we care, you buy a bag of chips, you open it in the room temperature, then you eat it again after 1 week, it becomes sweetie because of flavor reversion, we call it rancidity. In the second category of the food products, like fruit roll-up, what do you care? The color. The reason is at that time, there is another curve showed up, it's for Maillard reaction. Okay, how about here? We care about foodborne pathogen. So right before this class, I teach another class which is for the chemistry. We talk about chips, fruit roll-ups. We're going to talk about lipids oxidation, Maillard reaction, but here we don't care about this. We care about foodborne pathogen. So at the end of the day, what is water activity? Available water to be used by a bacteria. It's simple, but the story behind it is difficult. So that's what it is, especially the vapor pressure, what it is. So that's the explanation for that. Now, water activity in a food product, it's affected by a salt. So therefore, the concentration of sodium chloride will impact bacterial growth. Therefore, we have this curve comes out. This curve looks like confusing, but it's easier to understand. Based on the effects of sodium chloride on bacterial growth, we could categorize bacteria into halophiles and non-halophile. Most of the bacteria cannot survive with 0.2 mole of salt. So we know that salt is a natural antimicrobial. So be aware of that. Because salt will cause what kind of thing happen? Is cell wall shrinkage, is that right? And lose water. So salt is a natural antimicrobial. But there is some of the bacteria can grow in a certain amount of the salt solution. We call it halophiles. What is a good example of a halophiles? Staphylococcus aureus. They will widely exist on our skin surface. Our skin more or less have some salt. You know that when you're running 10 miles, 6 miles, let's say, you're sweating a lot. If you don't dry it, the second day or a couple of hours later, you see the crystal comes out. That's a salt. Even your t-shirt, you see a big white crystal. That's salt. The salt coming from the skin surfaces. So sodium chloride widely existing on the skin surface. Some bacteria can survive Staphylococcus aureus. Can you think about a place in the United States where the halophiles will be widely existing? Yes?
The Salt Lake City, Utah?
Yes, Salt Lake City, the Great Salt Lake at Utah, they have a big amount of the halophiles. So that's also environmental microorganism. They have the genes could be resistant to the salt impacts for the shrinkage of the cell wall system. Okay, I don't like that. It's in the summer. It's too too many mosquitoes in. So usually people go Yellowstone National Park. You fly to Salt Lake City, you drive 4 hours north, and you can have a fun at Yellowstone National Park to see those geobacillus and those thermophiles, hyperthermophiles. So when you go to Great Salt Lake City, Salt Lake, you can see the halophiles. Because remember those two places, you will know the impact of the water activity and the salt for microbial growth. Okay, next one. The amount or the impacts of the oxygen for bacterial growth. Okay, this sounds like complicated. So we want to explain to you a little bit simple. When you look at this table, it looks like woody and everything is there. So we want to make sure you understand that we want to make started from an easy one. Then we go some complicated. Okay, first of all, based on the requirements of the bacteria for the oxygen, we could simply to group them into 3 groups. Some of the bacteria must use oxygen to grow. This is called aerobic bacteria. Let's say Pseudomonas. They must use oxygen to grow. Some of the bacteria cannot grow in the presence of oxygen. We call it anaerobic bacteria. At this moment, the oxygen is the toxication. When they are exposed to oxygen, they will die. But most of the bacteria, especially we talk about those pathogens, like Listeria monocytogenes, Salmonella, E. coli, O157H7, Shigella, those can grow with without oxygen, but grow better with oxygen. This is called facultative. So basically say, there are 3 categories. So for example, aerobic bacteria, Pseudomonas. This is E. coli, let's say. The last one, we mentioned Clostridium. That's just 3 categories. Okay, then people find there are some other bacteria. They only need or grow in the limited amount of oxygen. So for example, only 5 to 10% of oxygen. Therefore gives you a bacterial category called microaerophilic. What a good example? Campylobacter. Campylobacter is a major pathogen in the chicken products, but it is very difficult to grow in the lab because it's microaerophilic. It's very ironic. It's a number 2 foodborne pathogen on the chicken meats, but difficult to grow in the lab. Now what we are missing? Aerotolerant. So we mentioned facultative bacteria can grow with or without oxygen, but grow better with oxygen. There is another category. They grow equally well with or without oxygen. This is called aerotolerant bacteria. Okay, then we're going to go a little bit deeper. So why some bacteria need oxygen? Why some bacteria cannot use oxygen? We're gonna go over to talk about the very basic biochemistry. We call it the electron transport chain. We will go detail when we talk about exam 3. Okay, electron transport chain. We gave you a very standard. Is NAD, go FAD, go FMN, and FES. It's a complex. Then we go coenzyme Q, then we go cytochroma C, cytochroma A, then we go cytochroma A3, and finally is oxygen. Okay, the electron gonna be electron transfer relate to the energy transfer. Okay, you need to know there's something. During this process, they are toxication material generated. Or toxication chemical will generate. What are they? H2O2, hydrogen oxide. So if we have to hydrolyze H2O2, we need the enzyme, the bacteria. It's called a catalase. Because the catalase can hydrolyze H2O2, become water, and release oxygen, which is bubbling. They also have another toxication will generate. Let's say superoxygen comes out. Then we need what? Superoxidase dismutase. Acronym is SOD. They could, let's say the O3 becomes O2 and release O1. Therefore, this tells us inside of the bacterial cell, they must have SOD and the catalase. They can survive in the presence of oxygen. If they don't have these two, they cannot survive in the presence of oxygen because they cannot hydrolyze hydrogen peroxide and superoxygen. Those are toxication material. Now, the amount of SOD and the catalase could be more or less. Therefore, they have a different category right here. Okay, that's what it is. It's very simple, but the story behind that is don't always think oxygen is good. Oxygen, during the process when they're using, they will generate toxication material. And the bacteria must have the enzyme to hydrolyze them. If they have both, that's good. If they don't have anything, oxygen is a toxication. If you have a certain amount, but more or less one of them, then we have a different category comes out. Let's say aerotolerant, strict anaerobic, facultative, those are comes out. Okay? So this is an interesting topic. Okay, anaerobic microbes, we can grow. There are two methods can grow. One is using a chamber. This is expensive, $25,000. There is a tube comes out with a gas resource, and you pumping oxygen. You pumped up oxygen and let it be composed by carbon dioxide. We also can do a chamber. We also can use a jar. This jar is not cheaper. It's $500 usually. Then we put a gas packer there. And the gas pack, we need to add 10 ml of water. So they will generate two items, which is hydrogen and the carbon dioxide. So what's the function of the hydrogen? Obviously, they're going to react with oxygen, generate the water. So the oxygen is gone. And we also see underneath the lock screw, there is a plug-in, which is a catalyst to let the reaction happen more quickly. And finally, we need to know the oxygen is gone. So how do we know the oxygen is gone? We need some of the indicator. Here we add methylene blue. And the methylene blue turns colorless. That means there is no oxygen. Another method we could do, we could add a resazurin, and the resazurin become colorless. There's also no oxygen there, in the absence of oxygen. Okay? So that's a method we can cultivate anaerobic bacteria. Microallophilic bacteria is similar because we have to make sure the oxygen amount is between 5 to 10%. So we have to control the resource of the oxygen. And here, instead of we using an anaerobic gas generator, we're using a microallophilic gas generator. It's the same thing. Just the amount of the oxygen is different. Here, we have to get rid of the whole oxygen. Microallophilic, we need lead a certain amount, but have to be very limited. Because if you more than 10%, it becomes intoxication. Now, why the reason? Because the catalyst is very low level. They cannot completely hydrolyze hydrogen peroxide. Okay, so that's something interesting we talk about. Biofilm, we already talked about. In the environments, we talked about the biofilm already, very briefly. Let's say the bench. I have a couple of cells there. Okay, I have a ground beef manufacturing there. I left the residue there. Ground beef is not sterilized. There are some bacteria. So we have some bacteria there. Then I forget to do the cleaning and the sanitizing. The second day I start to process another batch of the beef. And I only spray with water. I didn't use any of the soap or sanitizing. What happened? Those bacteria in a poor nutrition area, they're going to be accumulated. And then they're going through cell-to-cell communication. And we call it chlorine sensing. For chlorine sensing, there's different chemicals for gram-positive and gram-negative bacteria. Then they become sick and sick and sick. This whole thing is a matrix connected with polysaccharides and extracellular polysaccharides. And later on, what happened? Resistant to antimicrobials. And we talk about 200 parts per million chlorine can kill normal cells, we call it vegetative cells, but even if you're using 1,000 parts per million of chlorine, you may not can kill biofilms because they become resistant. And what we have to do, we need to know the morphology and the structure of the biofilm. Therefore, we rely on two important microscopes. Number one, laser confocal microscope, because we can see 3D images. Another tool we also can use to see 3D images is scanning electron microscope. Okay, so that's why the knowledge we could be connected with one we already being studied. Okay, so that's a biofilm for formation. Now, by the way, once the biofilm formed, they could stay there for a month, 2 months, 3 years, or forever. They will not naturally die. A bacterial cell in the broth, they could be died after certain times. So their growth curve is different. Nobody has been down there yet. It's quite interesting. Their stationary phase is extremely long. And also, if there is some cell is dislodged from this matrix, that will become a superbug. That could be a big contaminants comes from. And you also need to know there are some of the foodborne pathogens, they could not only in the food, they could be sprayed into the air, could become a human pathogen later. So that's something is interesting. That's why the sanitation and the cleaning is always very, very important. So every meat plants of the food plants, they have to develop a standard sanitation procedure. It is important. And also the machine design has to follow the sanitation rules, which means you have a sanitary machine design. You cannot have too much niche area. For example, can you touch here? You're not going to clean. Think about if this is a food processing. You're not going to clean here very well. You can clean the screen because it's all of the flat. But here, it's in so many niche area that is not easy to clean. Okay? So that's a biofilm we talk about. So we finished talking about here. We're going to go into the next slides. which is we will talk about the bacterial media. This is interesting, this is important. I'll give you some of the bacterial media sample next week. Here we're going to talk about this basic knowledge. Bacterial media is always important in the lab, and there are lots of the topics we could talk. Some concept is a little bit tricky, but we can understand. We don't have a lab, so I will show you something next week. Okay, first of all, bacteria culture media. Cultural media, I'll just say. Well, obviously, everybody knows bacteria can grow in the broth. So we have a liquid media. Broth. And we know bacteria can grow on the agar plates. It's a solid medium. However, you need to know, we also can grow bacteria with 1% of agar. That is called semi-solid. What is the function of semi-solid media? The semi-solid media, you will see the motility of the bacteria. So you inoculate a bacteria right in the middle. After you incubate 35 degrees Celsius 24 hours, if you see the bacteria stay in the line, which means there's not very strong motility. What else means their flagella is just one, is monotrichous. If you see the bacteria goes everywhere, that means the bacteria, the flagella is covered the whole body. That is called a petritrichous. It's Proteus bulgarius. So semi-solid agar, we widely used sometimes. Okay, this is based on the physical nature. That's the first one, based on the physical nature. Based on the chemical nature, we could be differentiated in the defined media and the complex media. Okay, this question is tricky. What means defined media? Every single chemical is well described. Otherwise, it's called complex media. So this gives you a very simple quiz. Okay, I have a medium. I have a bacterial medium. Okay, I have water. I have beef extract. Okay, let's just say 1 liter, beef extract 15 grams. I have peptone, 15 grams. I have sodium chloride, 25 grams. I have tryptone, 10 grams. Let's just say 1.5, 2.5, 2.5, 1.5. Okay, just bacterial media. You have ingredients, you have amount. Do you think it's a defined media or it's a complex media? Lots of people will say this is a defined media because you see the chemical is there. You see the ingredients is there, the amount is there, but it's not. Why? When we talk about defined media, every single chemical needs to well defined. And when you see the peptone, you don't know what inside. It's an extract of the polypeptides. Tryptone, the same thing. Beef extract, you don't know. It's like you buy a beef and stew and then you cook it. That's called beef extract. It's a brownish color of the water. So this is not a well-defined media. This is a complex media. So what is a defined media? The good example is on the top. So you may not like this chemistry, but I tell you one thing. Let's say this is a Bg11 media. You have potassium phosphates, magnesium sulfide, calcium chloride, citric acid, EDTA. All these are defined very well, the name and the amount. And I tell you one thing, Bg11 media is a poor nutrition media because only very basic chemistry is there, and that's a good media to grow biofilm in the lab. If you put a sliced coupon, which is a stainless steel coupon or plastic board, into a medium which is submerged with Bg11, biofilm will be formed. This is a complex medium. You see sodium chloride, peptone, sorbing digest called peptone. We don't even know what's inside. Okay, right here you have a casing. The pancreatic digestive casing. You don't know what's inside of the casing. So that's a complex medium. You see the beef extract? That's a complex medium. Okay, so just be careful. What's a defined media? Is every single chemical ingredient is well defined, which means the chemical construction needs to be there. The chemical name needs to be there. Otherwise, it's a complex medium. So this tells you some of the medium components. The peptone, the protein hydrolysis prepared by partial digest of various protein sources. Aqueous extracts, usually from beef or yeast, we call it beef or yeast extracts. Then the agar we already mentioned, it's a polysaccharides, liquid medium. Okay, it's founded by the great scientist Fanny Hesse, and coming from an idea from the French pudding. Bacteria can use it but cannot degrade it. Okay, functional medium. This slide has lots of we can talk. Why this is difficult to understand these medium? Because there's most of the category, and one medium is fits different category, and multiple different categories. So function group. So we want to talk about the function type of the medium. Okay, number one. Support medium. What is support medium? Simply to say, very easy, support bacterial growth. So, what are the examples? Troptic soil broth. Nutrient agar, nutrient medium, nutrient broth, and the common bacteria can grow. They can grow dramatically around 10 to the power of 8 cells per ml. That's huge. That's support medium. Second one is enriched medium. What is enriched media? The media containing certain ingredients will allow the bacteria grow dramatically. And how dramatically it is, they can grow up to 10 to the power of 10 cells per ml. One of the good examples of that is blood agar. Blood agar is red. You look at that, it's red. They containing 5% sheep blood. Why are they containing 5% sheep blood? Because back in 1970s, and the scientists find that sheep blood is the same characteristics as human blood. So they use sheep blood. Okay, now you see here. Chocolate agar. Oh, that's a good topic we're going to talk. Chocolate agar. Okay, first thing first. You need to know chocolate agar. There are no chocolate there. This is not you add a candy ball into the bacterial media, then grow it. There's no chocolate there. It is called chocolate-like agar. So what is that? That is 5% sheep blood agar you heated at 70 degrees Celsius, then turn a brownish color and looks like chocolate. Then people think you are smart, they deleted these. Okay, comes with chocolate agar. But it's confusing. Especially people doesn't know microbiology too much. They think you just put a candy bar there. Hershey like chocolate, put a cup of chocolates there. They know. It looks like chocolate, so we say chocolate agar. But chocolate agar is important. Why? They are for growing fastidious bacteria, which means the bacteria is very picky. They cannot grow very well or doesn't even grow in the normal bacteria, like chocolate soy blast, like nutrient blast. What are the examples? Neisseria meningitis, Haemophilus influenza, cause meningitis, cause childhood disease, meningitis, and Neisseria gonorrhea cause gonorrhea. We're going to mention about this in the exam too. Okay, lots of the passage we want to talk about. So that's chocolate agar, it's an enriched media. Okay, selective media. What is selective media? They add certain ingredients only favor certain bacterial grow.